It's been called the most successful theory in the entire history of science. I mean, it's been tested to an absolutely astonishing level of precision. Today, we're diving deep into the standard model of particle physics. I mean, it's the kind of question that can really keep you up at night, right? For literally centuries, it's what's driven scientists to just peel back layer after layer of reality. And what they've found, well, the answer is both beautifully simple and, honestly, profoundly strange. So to describe everything they found, physicists came up with this incredible framework. You guessed it, the Standard Model. The best way to think about it is like the ultimate recipe book for the cosmos. It lists all the fundamental ingredients and the rules, the forces that tell them how to interact. All right, so here's how we're going to break it all down. First, we'll cover what the model actually is. Then we'll meet the universe's building blocks, the particles, and the rules they all have to follow. We'll also look at some of the model's biggest wins. And finally, we'll get into the big cracks in the foundation, the stuff it just can't explain. Let's get into it. Okay, first section, a theory of almost everything. So what exactly is the Standard Model? I mean, where did this absolutely monumental idea even come from? Well, at its very core, it's our theory of matter and forces, and how they all connect. It's basically a giant classification system for every elementary particle we know about, and it describes how they interact using three, and that's a key number, three of the four fundamental forces. And believe me, this theory wasn't just dreamed up overnight. Nope, it was built piece by painful piece over decades. It really got going in the 60s when they unified two forces into one. Then came the theory for the strong force in the 70s, and after that, a whole series of just stunning experimental discoveries that kept proving the theory right, hitting these major milestones, like finding the top quark in '95, and of course, the big one, the Higgs boson in 2012. All right, up next, the building blocks of the universe itself. It's time to meet the cast of characters, the fundamental particles that make up you, me, and literally everything we can see. So it turns out every single particle fits into one of two big families. Think of them as two different teams. First, you've got the fermions. These are the matter particles, the bricks of the universe. They're a bit antisocial. No two fermions can ever be in the exact same state at the same time. And that's a good thing. It's why matter is solid, why you don't just fall through the floor. Then you have the bosons. These are the force particles, the messengers. And they're the total opposite. They love to bunch together. You can cram tons of them into the same state, which is how you get things like a powerful laser beam. But here's the part that just blows my mind. With this whole zoo of different particles, all the stable matter in the universe, I'm talking stars, planets, you, me, everything, it's all made from just three of these little guys, an up quark, a down quark, and an electron. That is it. The rest are kind of exotic extras. And here's the whole family photo. It looks complicated, but it's actually super organized. On the left, those are the fermions, the matter particles. See how they're split into three generations? That first generation, the up quark, down quark, and electron, that's our stuff. That's the stable matter. The other two generations, they're basically just heavier, unstable copies that existed in the early universe. Then, over on the right, you've got your bosons, the force carriers. You've got the photon for light and electricity, the gluon holding atomic nuclei together, the W and Z for radioactive decay, and then there's the odd one and out, the very special Higgs boson. Okay, so we've met the ingredients, now we need the rules of the kitchen. Let's look at the fundamental forces that govern this whole game, because having a bunch of particles is one thing, but you need the recipe that tells them what to do. So, as you can see here, the Standard Model does an amazing job describing three of the four fundamental forces that run the universe. You've got the strong force, which is, well, the strongest, then electromagnetism, and the weak force. But take a look at what's not really included. Gravity, the one we experience every single second of our lives? Yeah, that one's the big problem child. It doesn't fit in the model. Let's just take a couple of examples. The model perfectly explains the strong force. This is like the universe's superglue, holding quarks together inside protons and neutrons. It's incredibly powerful, but only works over teeny tiny distances. And then you have the electromagnetic force, which is what we're all familiar with. It's carried by photons, has an infinite range, and it's responsible for, well, basically all of chemistry, electricity, magnetism, and light itself. And then, of course, we have to talk about this superstar, this celebrity of the particle world, the Higgs boson.
Now, this one's different. It's not really a force carrier in the same way the others are. Instead, it's the particle version of a field that fills the entire universe. Think of it like cosmic molasses. As other particles try to move through this field, some of them get stuck or slowed down. And that resistance, that interaction, is what we perceive as mass. Okay, let's talk about the wins. Because the triumphs of this model are, and I'm not exaggerating, absolutely staggering. Its predictive power is what makes it, you could argue, the single most well-tested theory in the history of science. Right, and this is the crucial point. For more than 50 years, physicists have been throwing every test imaginable at this model, and almost every single time, it has passed with flying colors. Its predictions aren't just kinda right, they've been confirmed over and over again with mind-boggling precision. Here's a great example. Just based on the math, the theory made a really bold prediction. There should be exactly 3, not 2, not 4, 3 generations of matter particles. And sure enough, years later, experiments at particle colliders looked at how the Z boson decays and confirmed 3 generations, exactly as predicted. But really, the crowning achievement, the holy grail, was predicting the Higgs boson. The theory said it had to be there, decades before we had the technology to find it. And then, in 2012, after this massive global effort at the Large Hadron Collider, they found it. A new particle with a mass right around 125 giga-electron volts, smack dab in the middle of the window where the standard model said it should be. Just incredible. But, and this is a really big but, for all its incredible success, the standard model isn't the final story. It's not a theory of everything. It's a theory of almost everything. And the cracks in its foundation are some of the biggest, most profound mysteries in all of science. And these aren't just little gaps, they're huge. For starters, where's gravity? The model has nothing to say about it. Then there's dark matter. All our observations of space tell us that over 80% of the matter in the universe is this invisible, mysterious stuff, and the standard model doesn't have a single particle that fits the bill. It also can't fully explain why we're here at all, why the universe is made of matter and not an equal amount of antimatter, which should have annihilated everything. And even on its own turf, it has some issues. The original model predicted that neutrinos had no mass, but, oops, experiments showed they do, so we actually had to patch the model to fix that. It's just not the whole picture. So this leaves us with a final, really provocative thought. Is the standard model the end of the story, or is it just the first chapter? It is, without a doubt, a monumental human achievement. It's the best description we have of the subatomic world. But strangely enough, its biggest strength right now might be its flaws. Those very gaps, those unanswered questions, are what's driving physics forward today. The hunt is on, not to replace the standard model, but to build on top of its incredible foundation and discover what comes next, to write the next chapter in our cosmic story.